Hi! Welcome to the course Software Architecture, Meta and Solid Principles. I'm s.o.l.i.d, aka Engineer Spark from engineerspark.com, and I'll be leading you through the course. I began my career as a postgraduate student participating in Microsoft Imagine Cup contest. I've been working with .NET platform since 2003. I've been professionally architecting and implementing software for nearly 7 years, primarily based on the .NET platform. I'm passionate about building rich and powerful applications using modern technologies. I'm a certified specialist in Windows applications and service communication applications by Microsoft. And here is my teaching approach. No fluff, no ranting, no beating the air, I steam your time. The course material is succinct, yet comprehensive. All important concepts are covered. Particularly important topics are covered in depth. For absolute beginners, I offer my help on Skype absolutely free if requested. Take this course and you'll be satisfied. SOLID is an acronym which stands for SRP, OCP, LSP, and DIP. Another 5 acronyms. These 5 acronyms, in their turn, stand for Single Responsibility Principle, Open-Closed Principle, List of Substitution Principle, Interface Segregation Principle, and Dependency Inversion Principle. In this course, you'll learn how to apply solid and meta principles so that your application will live a long, healthy life. It means you are going to learn how to write code of the high quality, readable, understandable, and reliable. Improve your knowledge in object-oriented programming. Understand the meta principles on which all the other development principles are based. Understand the symptoms of code defects. Learn the foundations of solid principles. Learn how to detect the violations of solid principles and how to fix the problems. Learn how meta principles and solid principles are related to each other and how to find the balance between them. Despite the fact that C# is a very rich on features language, it's very common to see poorly designed and implemented applications in the real world. Programming language by itself does not guarantee that the architecture of an application will be great. In order to design and build maintainable software, we need to understand the principles of software development. This video course is exactly about how to achieve clean and maintainable software. You probably have already heard the following well-known statement: most code sucks. Well, this course is all about how to produce code which doesn't suck. Owning skills of producing a well-designed and well-implemented types is the prerequisite for the other developers to treat you as a decent professional. This course is aimed at middle and senior developers. Of course, some experience in C# is required. If you are a junior programmer, then I would say that you have to have at least half of a year of real-world experience in enterprise development. If you don't know how to work in Visual Studio, this course is not for you yet. There are plenty of code examples throughout this course, so that you will learn both theoretical and practical material. Starting with solid principles, we will go further to the meta principles. Going through the solid principles, you will also learn about the related patterns. Then we will get to the problem of contradictions between different principles. You'll learn about the relationships between solid principles and meta principles. In general, you'll learn in this course the 5 solid principles: SRP, OCP, LSP, ISP, and DIP. These are the solid principles. You'll learn the background problems that can be solved by a particular principle. You'll see the demonstrations in code. You'll learn the related patterns to every principle. Learning DIP, you will in addition learn what is dependency injection, inversion of control, IOC containers, how to build a simple IOC container, and what are the architectural implications of dependency injection. Here are the other topics you'll learn in this course. Dry, don't repeat yourself principle, KISS principle, keep it simple, stupid. Yagni principle, you ain't gonna need it. SOC principle, separation of concerns. CQS, command query separation principle, the law of Demeter, and POLA, principle of least astonishment. Information hiding and encapsulation. API development principles. Contradictions between s.o.l.i.d and Yagni. Contradictions between OCP and Yagni. What is architecture and design? You'll get tons of very important to know information. Enroll and start learning the solid and meta principles of building software systems. Hi, this is Engineer Spock, and I'll be leading you through the course. Before investigating what the solid principles are and how to apply them properly, we need to understand why do we need them at all. Solid principles are all about designing software. But what is design? How to define the design of software? Robert C. Martin, in his book Agile Principles, Patterns and Practices in C# stated that the design of software is source code itself. Martin Fowler wrote in his blog that architecture is the shape which code takes. Why is this so? Engineers produce documents, blueprints, which specify how to build a product. The only thing which truly specifies how software works is the source code. You may say that source code is the product, but the product is the running program, not the source code itself. Look at this from the following perspective. What is the input to a factory of circuit boards? Special electronic diagrams. In the case of software development, we have a factory which is called compiler. We feed it by the source code. A compiler builds software using the source code. And this leads to interesting thoughts regarding costs model of building software and, say, houses. When we build a house, it's much cheaper to create a good design up front rather than rebuild an entire house if we don't like the result. It's just not feasible to rebuild a house each time we don't like the result. The opposite we can say about software development. We can build binaries in a minute, roughly speaking. Big upfront design in case of software development is much more expensive than to draw a sketch, build the software and then tweak it along the way. The software development process is somewhat unique because conducting a big upfront design, we actually can't guarantee that we take into account all the possible requirements. The software is the fluid substance and requirements tend to change very quickly. Because of such a fluid, uncertain nature of software requirements, we need to constantly keep the design as clean as we can. Saying clean, I mean as maintainable as we can. To determine whether the source code is clean or not, we need to mark out the signs of design rotting. Developers refer to such signs as design smells. We can mark out 5 major design smells: rigidity, fragility, immobility, viscosity, and needless complexity. Let's define them one by one. The software is rigid if the cost of making a single change is very high. If something very simple takes many hours to implement, then the software is rigid. To overcome this problem, you might need to redesign the software. The primary source of rigidity is the high coupling between modules. When modules are tightly coupled, then it's very hard to introduce any changes with ease. The software is fragile when small changes in one module cause bugs appearance in other, sometimes even unrelated modules. This smell is also often caused by poorly designed relationships between modules. To overcome fragility, you need to isolate dependencies. The software is immobile when its components cannot be reused in other systems. Most of the time, we should be able to extract a component without too many efforts and adapt for using in another system. And what a surprise! This smell is most likely caused by tight coupling between components. To overcome this smell, you need to decouple components well. The software is viscous. When adding a single feature evokes dealing with tons of aspects, including, say, transport layer security, marshalling, and such things. In practice, you also can detect this smell by observing how to perform check-ins, checkouts, and merges. And most likely, the primary reason for this smell is a tight coupling between components. The software is needlessly complex when developers all the time are trying to forecast the future, anticipating upcoming changes, introducing excessive points of extension. Developers should concentrate on the current requirements. They should construct the supple architecture which can bend to be able to meet new requirements. Adding not needed points of extension yet is a bad practice, which leads to a needless complexity. Did you notice that almost all the smells are related to bad dependencies management? The major difference between object-oriented and not object-oriented languages is that o.o. languages are capable of harnessing the power of dynamic dispatch. By using virtual functions and interfaces, we can invert the dependencies. In o.o. languages, when we make a call, we don't know which object will handle that call. This is because of polymorphism or dynamic dispatch. So, the key to achieving a good architecture is to manage the dependencies well. And here we reach the point when we are ready to talk about SOLID principles. SOLID principles are 5 principles which can be referred to as dependency management principles. They are all about relationships and operations between objects. In this volume, we are going to dive deeply into the SOLID principles. The SOLID acronym was firstly introduced by Robert Martin, aka Uncle Bob. SOLID implies 5 principles of software development: SRP, Single Responsibility Principle; OCP, Open-Closed Principle; LSP, List of Substitution Principle; ISP, Interface Segregation Principle; and DIP, Dependency Inversion Principle. Many of these principles are based on the classic work of Bertrand Meyer. We are going to discuss all the principles one by one, looking at examples of poor design and how to fix it applying an appropriate principle. We will also notice the difference between Meyer's and Martin's definitions of some principles, what is also important for deep understanding. What I also want to emphasize is that SOLID principles are not bound to any technology. You can apply them in any programming language, in Java for example. Another point is that SOLID is not a goal by itself. The thing is that fully solid code is an oxymoron. It's impossible to write software which conforms solid in every single line. It's impossible to measure the solidness of the code base. SOLID are the 5 principles which help us to create better software. They involve a great deal of philosophy, and you might think that this is bad. Well, you can treat it as a flaw, but actually it's not. It's very important to feel this philosophy of designing software to become a better developer. And in this course, you'll see all the trade-offs developers face applying SOLID principles. You'll feel the philosophy of designing software. Okay, you've learned the common design smells and that we apply SOLID principles to remove that smells. In the next lecture, we will dive into SOLID principles starting with the outline of the SRP section. The Single Responsibility Principle, or SRP, in short states that every object should have a single responsibility, and that responsibility should be entirely encapsulated by the class. This definition is taken from Wikipedia. It's very hard to understand what does it mean. For example, the first two questions which come to my mind are how to define those responsibilities and how to calculate the number of responsibilities of a certain class. Such definitions are not very helpful from the practical perspective. Robert Martin, aka Uncle Bob, clarified this definition by saying that there should never be more than one reason for a class to change. Sounds much clearer, though it still needs further clarification. The responsibilities of a class can be treated as axes of change. It might be simpler to understand it as axes of changing requirements. For example, if a class implements logging and caching on its own, then it has at least two responsibilities. We also can view the responsibilities of a class from the perspective of its users. Any API has its users. These users are the source of changes. Understanding that, we can calculate how many axes of change a class has. For example, if a class deals with a database, then we have one axis of changes, since DB architects are those users who can request changes. If that class deals with salary reports as well, then we have two axes, since accountants are those who can request changes to reports. Apparently, the more responsibilities a class has, the more likely it's going to be changed. So, applying the SRP, we want to separate different concerns. A class should do one thing and do it well. By the way, the same principle can be applied at the level of modules. Modules should have only one logical responsibility. So, the SRP can be applied at different levels, at the function level, object level, and at the module level. Sometimes we find SRP violations at functions level. We refactor out different responsibilities to classes, and then we separate classes by their responsibilities into different modules, or assemblies if you wish. We discussed the SRP, but you might wonder how the concrete problem look like in real life caused by the SRP violation. Imagine the problems which are caused by the SRP violation. Here we have a class. Look at it. How many responsibilities does it have? I see at least 4 dependencies. Let's count them. The very first method, called charge, is responsible for interacting with a bank terminal. It should know how to initialize a device properly and send a corresponding command to it. The next method, called createReport, knows how to create a report about the payment transaction. It knows how to format all the data properly. Reports are usually so complex that there are 2 responsibilities may be hidden. One separate concern could be the process of creating a report, and the second is the formatting itself. If the process of creating an object is too complex, then very often we treat it as a separate concern and we tend to isolate such responsibilities by extracting a factory class which knows all the details about report's creation. The third method, called printReport, knows how to deal with printer's driver and how to send commands to it. And finally, the save payment method is responsible for interacting with a database to save all the data about a payment transaction. We often have a hidden responsibility in such cases. We can call that responsibility orchestration. We often need some high-level object which knows how to integrate all the responsibilities together. Now imagine that we need to change the payment processing and saving to a database simultaneously. 2 different programmers are responsible for these 2 different parts of the system. Unfortunately, these 2 different parts reside in the same class. As a result, these 2 programmers need to change the same class, and in the end, They will need to merge their changes to finish a check-in. Aside from this problem, such classes which accumulate many responsibilities are hard to understand. Such classes become a big ball of mud. One day, no one will understand what the hell is going on in that class. Another problem is that sometimes we need to introduce changes into only one responsibility. Let's say we need to change the payment processing. Because several responsibilities reside in the single object, classes which represent them will also be recompiled and redeployed. Nowadays, this problem in the majority of cases may seem like not a problem at all. But for example, if we develop in C++, then it can cause some issues in the end. The thing is that such careless attitude to dependencies management leads to a long compilation time. C++ is much harder to compile, so this problem is very important in such cases. If we had isolated these dependencies in different modules, we would have needed to recompile and redeploy only one module, the module which has been changed. So, when SRP is violated, responsibilities start to collate with each other, what means that they become coupled. What we need to strive to do is to gather all the same responsibilities together and separate from each other those which are different. When we gather the same responsibilities, we try to achieve the so-called high cohesion. When we separate different responsibilities, we try to achieve low coupling. At the level of functions, cohesion means the following. A set of functions, an interface, is considered cohesive when each function is closely related to another. Coupling indicates how dependent modules are on the inner workings of each other. Tightly coupled modules rely extensively on the specific state of each other, sharing variables and many types. Loosely coupled modules are fairly independent. They have a few well-named APIs and share a limited amount of or no data at all. Okay, let's look at the problem of SRP violation in Visual Studio on another example. Let's consider an example of SRP violation. In this example, we deal with an application which allows users to buy tickets on suburban trains. Pretend that the system we develop works on the website and on the point-of-service terminals. Let's say also that we develop an MVVM-based application, and somewhere in the code base we have the payment module, which provides the ability to buy a ticket. If you look at the API of the payment module, you will see that it exposes the buy ticket method with 3 arguments of the following types. Ticket details, which contains details like the station of departure and arrival, the price, and so on. Payment details contains the paying method. A user can pay by cash or by credit card. It also can contain any other relevant information. The action is the parameter, which is used in the following case. A user tries to pay by cash in the POS terminal. He overpays. POS terminal tries to dispense the change, but it doesn't have enough money to dispense all the change. So we need to return the remainder to the mobile phone of a user. The client's code provides the handler of such situation by passing it via that parameter of type action. This is a real case from my practice. In the body of the method, we check if a user requested to pay via a credit card, and in such case, we call the charge card method, passing the ticket and payment parameters. The charge card method creates some gateway through which we perform the charge operation. If a user wants to pay by cash, we call the accept cash and then dispense change methods. In the accept cash method, we would initialize devices which accept money, but Here we just have a simple stub for the sake of simplicity. The dispense change method checks if a user overpaid and in such case initiates the process of dispensing the change. I omitted another responsibility, printing the ticket on the paper, in case of purchasing a ticket in a POS terminal. This is for the sake of simplicity, but you can imagine that in real life this method could be even more complex. This example is just fine for our investigation of the problem. What's wrong with the buy ticket method? It clearly violates the single responsibility principle. The two different mechanisms, paying by a credit card and by cash, are coupled. Let's look at the diagram of dependencies. You can see here that the payment model is the meat. It is the central part of the design, which is responsible for everything. It depends on payment details, processing center gateway, and ticket details. In other words, it knows everything. We have already discussed the possible unfortunate consequences of such a design. Let's separate the feature of paying by credit card from the feature of paying by cash. I prepared the refactored version. Let's look at it. At first, I wanted to abstract away the process of buying a ticket, so I created an abstract class payment module with an abstract method buy_ticket. This class also contains the ticket details as a protected field, since we need ticket details to be visible from within all the inheritors. Adding ticket details here is not necessary, but if we want to implement some shared business logic which uses ticket details, then this could be beneficial. Again, this is a trade-off. Everything depends on the concrete requirements of a concrete application. The first inheritor I implemented was the online payment class. In the constructor, it accepts ticket details and payment details, which are required only in case of payment by credit card. In the constructor's body, we set the payment property and create the bank gateway, which implements the I can pay via credit card interface. This interface defines only one method right now, the charge card. And again, here's a trade-off. We can avoid creating a separate interface, but if we know for sure or expect with a high probability that shortly we will implement other bank gateways, or we already have different implementations of the bank gateway, then it's meaningful to introduce an interface to decouple different implementations of bank gateways from each other. We could also cram all the implementations into a single class, except a parameter which would indicate which gateway to use, but that most likely would lead to overcomplicated code. Developers often refer to such code as to a big ball of mud. Take a notice that we explicitly create a concrete implementation of the I can pay via credit card interface, what means that we can't use here other implementation if they exist. This is a topic which we will discuss in the dependency inversion principle section. So wait a little bit and you'll get the answer. Okay, let's look at another inheritor. Here we have the post-terminal payment class. In the constructor, it accepts the ticket details and a callback to notify the caller about the necessity to return the remainder of change to the mobile phone of a user. This class implements the I can operate with cash interface, which exposes two methods: accept cash and dispense change. Inheritance via classes and interfaces provides to us the opportunity to build a very flexible design. It might be better to accept the I can operate with cash in the constructor, and frankly I think that it would be better most likely, but I want to stress that we can face a situation when we don't want to create a separate class. Maybe we want to make the post-terminal payment substitutable by another implementation of the I can operate with cash interface. When we decouple a responsibility by an interface and require that interface in a constructor of the class which takes the role of an orchestrator, we rely on a composition rather than on inheritance. Composition doesn't impose such restrictions as a direct inheritance does. Remember that inheritance couples the parent and child classes very tight. Child classes take a great burden of satisfying the parent's API and parent's invariants. We will be talking about invariants in the LSP section in more details. Look at the diagram again. Now we have two different classes which orchestrate all the things. These are post-terminal payment and online payment classes. Each of them takes a concrete responsibility. Post-terminal payment doesn't know anything about bank gateways. Online payment doesn't know anything about how to accept and dispense cash. Payment model is on top of the hierarchy, and it doesn't depend on anything except ticket details. Now we have 2 points of extension. I can operate with cash and I can pay via credit card. You can argue that now we have more classes and the design now even more complex than it was before the refactoring. And I can both agree and disagree with you. I want to stress again that everything depends on the requirements of an application. If you see that a class or a method is too fat and it's hard to understand, then it would be better to refactor it applying SOL.i.d principles. Sometimes we can apply only one of the SOL.i.d principles. But more often we apply more than one principle to perform a refactoring. Okay, you've learned how to apply SRP to perform a refactoring. Now I want you to look at more simple examples of the SRP violation. You'll see common smells which indicate that the SRP is violated. Here we have a method named getReport. In the body, we can see that it gathers some statistical data, then creates formatted strings and put them together. How do you think? Does this method violate SRP? This method clearly violates the SRP. It has two responsibilities. The first one, gathering the statistical data, and the second one is formatting. Junior programmers very often mix the formatting responsibility with business logic. Of course, sometimes, if we are sure for 99% that formatting will never be changed and it doesn't interfere with the other code, we can leave such code as it is. But more likely it would be better to at least extract formatting into a separate method. Let's look at another case. Here we have the find alarm device. It scans through serial ports trying to find the device, and if it finds it, it sets a global state by setting the alarm can be used property. How do you think? Does this method violate the SRP? This method clearly violates the SRP. It mixes the policy or business logic with mechanics. Remember that high-level policy should be decoupled from the low-level details. We could refactor it by introducing a special class which is responsible for interacting with global state. That class could receive notifications via events or any other appropriate way. Let's look at the next case. Here we have the method named drawRectangle. It calculates where to draw a rectangle, then picks a color and draws the rectangle, filling it with that color. How do you think? Does this method violate the SRP? This case is trickier than previous ones. The previous examples demonstrate very popular smells of violating the SRP. It's harder to determine the responsibilities here. The number of actual responsibilities always depend on the users. Are there actors or users who might be interested in managing the color? If there are such users, then it might be better to separate the responsibility of picking a color. A separate interesting question is whether the creation of an object is itself a responsibility or not. We're not going to answer this question in this section. We will keep it for the section about DIP. In the end, I also want to list some common SRP violations. First, mixing logic and infrastructure when business logic is mixed with views or a persistence layer. Class or a module serves different layers, calculates income and sends emails, parses XML and analyzes the results. Before going further, I just want to skim through one function I faced in practice. This function is about 5,000 lines long. It consists of switch case and if statements. It relies on them massively. This is a real hell and an extreme example of SRP violation. I wanted to show you this example just for fun. The majority of developers don't believe me when I say that I've seen such a function. No, such functions exist, and developers who write such functions also exist, as you may guess. In the next lecture, I want to say a couple of words regarding design patterns related to the SRP. Sometimes we apply the SRP to refactor a part of a system, and we end up with many small classes. Clients of such an API may struggle with understanding the whole part of the system because they need to understand the relationships between all that small classes. It's not that bad as it sounds. As I've already said, there is always a trade-off between different solutions. In such cases, the Facade pattern may come to the rescue. It wraps all those little classes, just delegating all the responsibilities to them. It doesn't make the Facade a violator of the SRP. The only responsibility of such a Facade is to bring the functionality required by a client together. It may seem like it violates the SRP, since we will see the responsibilities of different layers reflected in the API of the Facade. But as I said, aggregating the functionality which allows solving a single client's problem is not bad. It simplifies the interaction process with the system from the client's perspective, and that's all, nothing more. So, there are two main reasons for using the Facade pattern. Provide for a client a simple API for interaction with a set of complex objects, and provide for a client a cleaner API for interaction with poorly designed API. Sometimes it's much easier to roll out a Facade rather than rewrite a poorly designed part of a system, and this is what the second point is about. From the SRP's perspective, we're interested in the example which demonstrates the first reason of using the Facade pattern. Here you can see a diagram which demonstrates an example of the Facade pattern. You can see here that the purchase Facade class depends on all the other classes. It contains, or in other words, wraps all these classes. The wrapped entities don't have to be classes, they could be interfaces as well. So imagine that initially a client was dependent on all these classes. We introduced the Facade to simplify the interaction process with the system. If a client depends only on the Facade, it doesn't have to directly interact with many classes. Let's switch to Visual Studio, where I'll show this example in code. Here is an example. Let's say we have a client which uses our system to sell goods from the store online. So, the client's code looks like this. It creates a customer object using the static method findCustomer, passing in the customer ID. After that, it creates an order through the static find method of the stock class, passing in the good ID. Then it gets the info about the customer's credit card, creates the bank gateway and calls the charge card, passing required parameters. I bet such interaction process looks like a mockery. Indeed, it's our duty to simplify the lives of our clients. So, we can create a facade which hides all these details of processing a purchase. I've created here the purchase facade class, which exposes a single method. This method requires two integer parameters and hides all the details inside its body. Now, a client doesn't have to know about all the classes and how to interact with them, which methods to call. The only thing a client should know is that it can just create a facade and call one method to achieve the goal. That's all. There are many patterns which are related to SRP. Decorator and composite patterns are also very closely related to the SRP. According to the definition from the Gang of Four book, composite pattern allows to compose objects into tree structures to represent part-whole hierarchies. Composite pattern lets clients treat individual objects and compositions of objects uniformly. According to the same book, the decorator pattern allows the behavior to be added to an individual object, either statically or dynamically, without affecting the behavior of other objects from the same class. The decorator pattern is often useful for adhering to the single responsibility principle, as it allows functionality to be divided between classes with unique areas of concern. We're not going to discuss design patterns in this course deeply, so I can just recommend you some sources to look at to get a deeper understanding of design patterns and their relationship to SOLID principles. Congratulations! In this section you learned the single responsibility principle, what this principle is about and how to adhere to this principle to make the code base more maintainable. So, let's sum up. I like the definition of the SRP from Uncle Bob. There should never be more than one reason for a class to change. Applying SRP, we want to separate different concerns. A class should do one thing and do it well. SRP can be applied at different levels, at the object level, at function level, and module level. Classes which accumulate many responsibilities are hard to understand. When SRP is violated, responsibilities start to collate with each other, what means that they become coupled. At the same time, when abusing the SRP, you can end up with too many small classes and methods with business logic spread among them. In such a case, you might want to apply the facade pattern we discussed in the Related Patterns lecture. Remember that those modules which are expected to change frequently should be isolated from the other parts of the system. Concerning this problem, I also want to add that, in general, I agree that using interfaces with a single implementation can lead to less maintainable code, but sometimes the isolation provided by such design is exactly what we need to isolate a module that changes frequently. In the next section, we're going to learn the open-closed principle, one of the most misunderstood principles.